Hello physics students, this is Mr. Stockbridge. As we continue our studies in temperature, heat, and a little bit of thermodynamics, it's time for us to talk about changing phases. Now for the most part, changing phases are going to be very familiar to you. There are a couple of different types of phase changes, and these go back to elementary school science, and you've seen them in everyday life as well. We have freezing, melting, evaporation or boiling, or almost synonymous. We're not going to split hairs and talk about the differences between those two. We have condensation, and we have the least known type of phase change, which is going to be sublimation. We're not going to talk too much about sublimation. We're going to more or less stick with the main transitions that we have up here. Now, for the most part, when people think of changing phases, they think of pairings. For example, freezing and melting are opposite processes, so they get paired together. Same thing with evaporation and condensation. Opposite processes, so people think of them together. We're going to shift things a little bit, and instead of talking about pairings, we're going to look at things from the perspective of which transitions result in cooling and which ones result in warming. Now, before we get into this, just like we have conservation of energy, we're going to see that show up here in thermodynamics as well. Energy can't be created or destroyed, and temperature is ultimately just a measurement of the energy in a system. So when we talk about cooling or heating, we have to think of two different sides of a coin. Anytime something cools, we have to think about the object and the object's environment. So, for example, when we talk about melting, when we melt a solid and it becomes a liquid, that requires more energy to go into the substance, but that means that energy has to come out of the surroundings in order to accomplish that. This is why we say that melting is a cooling process, is because that's where we're focused on its effect on the surroundings, not its effect on the object. So melting is one transition that results in cooling. Evaporation is also another one that results in cooling. When people sweat during the summer, we're taking liquid and we're using the energy or the heat coming off of our bodies to change the phase and switch it from a liquid into a gas. So the water is gaining energy, but the environment has to lose it for that to be accomplished, and that's why evaporation is a cooling process. Again, we're not going to talk too much about sublimation. Transitions that warm the environment. When we freeze something, it takes work to get from a liquid phase down to molecules being held more closely together in a solid phase. So the object is cooling down, but that requires an input of energy from the environment, which is why we say that freezing will warm the environment slightly even as it cools the object. And again, the same thing of condensation, going from a gas down to a liquid. Here we have everything written out in bullet point form, but let's go ahead and take a look at this in graphic form. Here we have a slight modification of one of the graphics taken from the OpenStax college physics textbook. And we're going to look at the fact that cooling the object warms the surroundings. Let's start on the right, because cooling is going to go from gas down to a solid. So if we're cooling the object, gases have a lot of kinetic energy in individual particles. As we cool and it becomes a liquid, these particles or molecules have less energy per unit than they did previously. Well, again, where does that energy go? If the energy is leaving the substance, it has to be entering the environment or the surroundings. And the same thing happens as we move from liquids and freeze them down into solids. In order to produce that phase change, we have to alter the energy in the surroundings. Now, the next one, we're just simply going to take a look at the opposite direction. So if we're warming the object, we're going to start over here on the solid. As we put energy into the object, into the material, it speeds up the molecular motion. Where does that energy come from? It comes from the surroundings. This is why if you're out in a parking lot after a big storm, but the snow has been plowed, the corners of the parking lot, off where the snow piles are deepest, are going to be cooler than out in the main body of the parking lot, is because the process of melting that snow into water requires energy to be drawn from the environment to accomplish the change. And again, same thing here, as we not necessarily boil, but let's say we evaporate that liquid into a gas. Again, it requires energy going into the material, but out of the surroundings. One of the classic labs in chemistry is a lab that will ultimately produce a graph similar to this one. Let's go ahead and take a look. Up here on the y-axis, we have change in temperature. So whatever material it is that we're dealing with, and here you can see we're basically just dealing with water, H2O. The temperature rises the further up we go here. Well, what does it take to do that? We have to heat the object. Down here on the x-axis, it shows how much energy is being put into the water in order to cause those temperature changes. And we see that we don't have a straight line the entire time. As we start from a solid and we begin to warm, once you get up to 0 degrees Celsius or 32 degrees Fahrenheit, notice how even though we continue to put more energy into the system, the temperature of the ice and water doesn't change. Why is that? Again, conservation of energy. It has to be going somewhere. If that energy is not being used to change the temperature of the substance, then it's being used to change the phase. It takes energy to get from a solid and transition it into a liquid. So this flat region of the graph right here represents the period of melting. Once the line starts taking off again, now there is no phase transition. This is just water, and the water is going to continue changing temperature all the way up until we hit that next transition point, going from a water to a gas. And again, no matter how much energy we put into the water, the temperature is going to remain unchanged until all of that liquid has been transitioned into a gaseous state, into the gas phase. So if someone says that it takes work to start with ice and melt it into water and then boil it off into steam, yeah, they're correct. Because remember, energy is the ability to do work, and here that work is simply changing the phase. These flat regions of the graph, right here and right here, are where we see those phase transitions happening. The final piece of thermodynamic joy is going to be phase diagrams. Let's look at the anatomy of the graph before we start getting into the details of what it means. First of all, a phase diagram is always for a specific molecule. In our case, we're looking at water. Over here on the y-axis, we have an increase in pressure from bottom to top. The numbers seem to make random jumps there, but that's only because this diagram has been scaled so that all of the things that we need to fit on the graph will actually fit on the screen. Down here for temperature, again, it's been scaled so that everything fits, and we have an increase of temperature from left to right. S represents the solid phase. Everything above this red line and to the left of this red line is water in a solid phase. So this is ice. In between these two, in the upper region of the graph, that's liquid water. And then water vapor, or water as a gas, is everything under this line and under this line, all the way over to the left and then even off to the right. Now, as far as what's happening within the graph, the specific phase that exists always depends on the environment. And the two things about the environment that matter most are the pressure and the temperature. Remember, temperature is a measurement of what the average kinetic energy in the molecule is. So while the kinetic energy has these molecules trying to fly away from each other, pressure is trying to push all of these molecules back together. Although there is some chemical attraction between molecules, most of what holds them together in close proximity is going to be the pressure of other surrounding molecules. Let's take a look at a quick example. Say you have a glass of water, or I'm sorry, a glass of ice as a solid, and we're not going to change the temperature, we're just going to change the pressure, which is the same as dropping straight down on the graph. At a certain point, the pressure is low enough that we go from a solid to a vapor over here. This actually happens on the surface of Mars. Mars has so little atmospheric pressure that you can boil water at 35 degrees Fahrenheit, simply because there's not enough pressure from surrounding molecules to hold individual atoms and molecules in place in the solid. Gradually, all of the molecules and atoms on the surface of that piece of ice will just kind of wander away in gaseous form. Same thing can happen with a liquid. If you keep the temperature constant, but you keep dropping the pressure, you will eventually transition from a liquid off into a vapor again. Now, as far as horizontal lines, those make more sense. We're kind of used to that. If you keep the pressure constant but increase temperature, that's the same as traveling horizontally on the graph. You move from a solid to a liquid, and if you keep heating it enough, you go from a liquid to a vapor or a gas. No surprise there. A couple of interesting points on the phase diagram. The triple point right here is where all of the red lines intersect. At this one specific combination of pressure and temperature in the environment, you can have all three phases, solid, liquid, and gas, existing simultaneously. The red lines represent the regions where you can only have two phases at a time. So at all of the different pressure temperature combinations along this red line, we can have solids transitioning into vapors. Along this one, we have solids transitioning into liquid, or vice versa. And of course, along the final one, we have liquid and gas existing at the same time along all these pressure temperature combinations. The critical point, far up and to the right here on the graph, is interesting because that's where pressure doesn't really matter anymore. At this point, from here on to the right on the graph, the temperature is so high that the substance, again, water, can only exist as a gas. No matter how much you increase the pressure at this point, you're never going to be able to push it back down into the liquid phase. So a phase diagram helps us analyze what the environmental conditions are and how they help to determine what specific phase of any particular molecule or substance that we're looking at. With that, I think we've gone on long enough. Please feel free to ask questions if you have them, or replay this video to see if there's something you missed.